And today, I will talk about a system, interactive system of elephant random walks. There are many results about the usual random walk, and we give some analogies for elephant random. There are many results of for a random, usual standard random walk. It is very nice to generalize elephant random walk. Some application is correct and something is wrong. But it is very interesting to take for each model. And first, introduce elephant random walk. And maybe many of them know this definition, but I want to explain them explicitly. And the elephant random walk is introduced by Schutz and Trimper. And at first x1 equal +1 with probability. Here, I assume this is half. And -1 with probability 1, half. And xn is determined inductively as xun with probability p. P is called memory parameter. And minus xun with probability 1 minus p. And un uniform distribution on the 1 to n, and n is integer natural number, which is independent of the previous xk, k equal 1 to n. And the elephant random walk is the time inhomogeneous Markov process. We find the summation of xk's Sn. And I want to check why this is Markov. And there is the process depends on the memory, and upon nn plus and n minus n. This is a number of pluses until n, 1 to n, and minus until n. And the process n equal, of course, this is trivial equation. And the point is, the step is just 1 and -1. Then Sn equal the number of plus minus 1. Cross this simple relation, we can get the ratio. The point is un is uniform distribution. We need from the memory, we need the ratio of plus and -1. And this value can be obtained from the position at n and time. Then if you know the position at time n, we can get this ratio. From this process is Markov. Just the position, we can get the transition. But we have to remind that it depends on the transition depends on the starting point. Because the step is plus and minus. If you start the 1 and the memory a little bit change, and it depends. Position depends on the initial position. And we have to remind this point. This transition depends on the initial value. Later, I will consider this. And another representation of this, instead of memory parameter p, we use alpha equal 2p minus 1. It is called reinforced random walk. And Yn is IID, such that Yn equal 1, and with probability half, and Yn equal -1 with probability half. And consider the process. P equal alpha plus 1 over 2, and between half and 1, and x1 equal y1. Xn is defined like that. And with the probability alpha, and xn plus 1 equal xun. And with probability 1 minus alpha, yn plus 1. This is related random walk. And if you choose this one, this is depend on the previous movement. And if the plus is, there are many pluses, the process wants to go +1. And the other one, this is positive reinforcement. And if P is like that, and between 0 and half, and this is given like that, this is a, if with the probability minus alpha is in this case negative, alpha is between, minus alpha between 0 and 1. With probability minus alpha, xn plus 1 equal minus xun, and opposite direction. Reinforcement in the opposite direction against the previous steps. And this is random walk case. Yes, random walk and reinforcement. This is positive reinforcement, and this is negative reinforcement. Right? This is, we have two kinds of explanation of this process. Both are, of course, same, but sometimes one of them is very convenient to understand the model. And the Schutz and Trimper calculate its variance, and they show the phase transition of this model. This is very important point. PC is 3/4, and P is greater than PC. This is super diffusive. And if PC is P is less than PC, is diffusive. The point is the Harman, this is a ratio of that. And if n to infinity, this converges to half in any case. But the order, speed of this is important. And they calculate some estimate of that. And get these things. And to study this model, martingale argument is very important. And by embedding theorem into Brownian motion and time change, it is very important to check the absorptive behavior of time change. And finally, we can get this kind of things. And if super diffusive case, we can get this functional central theory. And this is the diffusion scaling. WT is converged in the Skorhoff distribution. Then WT is non-zero Gaussian process starting from the origin. And covariance is given like that. If alpha equals 0, this is exactly the Brownian motion. Right? And a critical case, this is the diffusion case. At critical case, 3/4, and they proved Bertheldi and Rosal Oritz proved that getting different. I will explain later a little bit. And convergence and functional central limit theorem. And super diffusive case and the convergence of this is a little smaller, not plus epsilon, but there are some fluctuation. Then this process does not converge to a Brownian motion or a Gaussian process. But this L is a non-Gaussian process, and we know that J proves that L is positive with property 1, and L has density also. But we don't know the exact distribution of that. But they calculate some moments for each n. They get this recursive formula with some moments, and that's very complicated. And we know that we don't know the relation between the previous and well-known distribution. Maybe this is new process, new distribution, new random radials, and this one. Anyway, we are interested in this one. And interacting party system. This is a candidate and the interacting system. I think this is very interesting. And first one is the exclusion condition. And for random walk case, this is exclusion process. Exclusion is very easy. There are many particles on that, and which moves according to the random walk. And the exclusion condition is if the particle moves this one, and there exists a particle, they cannot. The jump is suppressed. If they want to move this, they can move. Okay. And there are many results concerning this exclusion process. And we want to extend this process for elephant random, right? But it is very clear. In this case, elephant random, we cannot move this. But the different from the original one, and memory, this part that cannot move. This means that the memory is 0. In addition, the memory is plus and minus 1, and new memory, which is also stop. And the model becomes very complicated. If the zeros increase very quickly, the movement of particles is slow, and in some cases is stop unfair. But I don't know the mathematical result on this model. And in physics, they prove some result. They modify this model and try to, by a simulation, they get some result and start on something. But this is very different from the original one. And next model is non-colliding condition. In random walk case, this is a vicious walk. I will explain this later. And the model for elephant random walk is today's problem. We are interested in non-colliding elephant random walk. I will explain it. And recently, there are many results interaction between memories. And they consider the model, or each particle has memory, of course. And to get to consider the movement, they choose some memory of another particle and their interaction between. And two elephant case. This is just two articles. Hideki and Queen and McCrory consider this model and get the sum limit theorem, central theorem, something. And the very interesting case is many elephants on Z3 with graph-based shared memory. This is shown by Subhra, and this is ICTS. This is quite general and very interesting. And the relation and the memory relation between the particle is given by like the graph and such connection in data. But this is very interesting. I recommend it. And okay, I will explain the vicious circle. Vicious circle is introduced by Michael Fisher in physics, statistical physics. And this is just conditional random walk. Average J's, the n-independent symmetric simple random walks, starting from Zi's, like that. And this is non-collide condition. This is a set no particle collide, like that. And consider the conditional distribution of the process under this set, non-collide set. It's very simple. Just consider the process and move without collide. And many things are studied. And the state space is like that. The difference, the position of particle between the difference of the distance of the two particles is 2n, even numbers. And let Pxy be the transition function of the symmetric simple random walk. And the probability is that absorbing space and while chamber something, and that n random walk starting from Z is the sequence Z1, Z2, n-dimensional set, and arrives at Y at time t without colliding each other is given by the determinant of each part. This is Curry-McGregor formula, very old formula, same age as 1959, very old result. But very important result, and many papers refer this result. This is also in the some many things concerning this one. And
yes,
please.
This formula on the right doesn't depend on capital T. There is an index capital T in sub-index.
T time transition, sorry.
Ah, there's
sorry,
yeah.
Okay,
thank you.
Yeah, T is here. Just in one particle transition, we can get n particle transition. This is very, thank you very much. And the conditional probability given that summation, this one, this is summation over all realization of this. This is the probability that no particle collide. This is the probability. This is exactly as a representation of vicious walks. And 20 years ago, Makoto Katori and I proved these things. And after consider this vicious walker, and under the diffusion scaling, the process converges to temporary inhomogeneous diffusion process X, and this satisfies this one. This is Markov, but this is quite complicated. This is inhomogeneous. And here, NTZ is a probability that each pair of coordinate of and Brownian motion starting from Z do not collide until T. This kind of. This diffusion is just Brownian, non-colliding Brownian motion until T, like that. Is here. And the next is if T to infinity, we can get this one. And according N, we make T n infinity, larger and larger. This limit process is temporary homogeneous diffusion process by T, and like that. This is very famous. What is Dyson's Brownian motion, and the Brownian motion plus the 1 over, this is the reverse of the distance of the process. This is a repulsive force. And Dyson's Brownian motion with beta equal 2. And this is also where this in the H. One element deployment is the harmonic function of absorbing Brownian motion, and this is H transform of this. And this result is not the original of this paper. This is just this. There are many results around this, and by using many techniques, and many people prove this. And this is that of our own, and we can get this result from this. And the important point, and this is not important, but if infinity, the process is change, and this is Dyson's Brownian motion. This distribution is absolutely continuous with this, and density is given by the 1 over the inverse, 1 over H. H is van der Waals determinant at the end point. Density is given the angle like this. And in one-dimensional case, this is for the Brownian meander. This is called three-dimensional Bessel process. This, right? If you consider the two particles and the distance between them, this is one-dimensional case, and the first one is Brownian meander. The second one is a Bessel, three-dimensional Bessel. And non-colliding elephant walk, and a standard elephant random walk is a temporary inhomogeneous Markov process. Okay, and we can apply the Karim-Maclay formula, and what has a transition density depending on the initial point. This is a problem, and Karim-Maclay needs the property is that if two particles collide, the transition of each particle is the same, because this is just kind of reflection principle argument, and we need the transition the same. And but original elephant random walk depends on the initial value. And I want to modify the model a little bit and to consider the elephant random walk from the origin. And in the inventory, they give that. And at time T, this condition, we consider the elephant random from this. And this is independent. This is depending on the initial value, they have many memory past before. Yes. The initial point, they have a memory. This is just like that, conditional distribution of that. Then this is same transition density. And we consider the independent case. and Karimakura formula, like that. This is T here. Okay. ST at time T, this is YJ. Also, your comment is very important. And probability of non-colliding elephant random walk is given like. And we want the diffusion scaling limit of the process. This is, but the difficult point is this goes to 0. Oh, okay.
So the mathematical formula, is that applicable to even elephant random?
Yeah, in this case, we are Karimakura formula is given for time of inhomogeneous random walk and especially homogeneous walks. But the transition at the point is the same. This is very important. Then we can apply, in this case, we can apply that. Okay. The point is this not easy because this term converges to as T to infinity. And this is one particular system, and we want to explain the precise convergence of functional situation first. And the P is diffusive case, and we know that. We know that convergence, and this case, these people prove this one. And this WT is a Gaussian process, and conversion is like that before, but we have another representation like that. This is scale and time scaling of Brownian motion. This is very, as a process, this is same in distribution. And another representation, W satisfy the following stochastic differential equation. The point is, this is Brownian motion. This is not time and very a little bit complicated, but this case is drift is given like that. And this depends on T. T goes to bigger and bigger, so the drift is smaller and smaller. And there are very interesting results by Belt 1. If you consider one elephant random walk, this is recurrent. They come back here. First, the fitting time as expectation, some kind of positive recurrence. And second is no. This is not positive. Expectation is infinite. This kind of since related to this one. And this kind of drift, this is some kind of drift. And if alpha is negative, the process goes to the origin, quite strong power. But this is depends on T, and the drift becomes smaller and smaller. And first hitting time is finite expectation, but second, third, the expectation is infinite. Narrow recurrent. And this is the critical case. They have this kind of thing. This is not process every some random variable and square root T and general and super diffusive case EP and L. Just and it is trivial to consider the non-colliding processes because this is itself non-colliding. Right? Just this is density, and for each particle has a different value, and this different coefficient. This is this joint and this is a process. And the point is, we are considering non-colliding Brownian motion is given by like that, and by using formula given previously, and Dyson-Brownian and so on. And the process is given like that. Then non-colliding of this process, reinforced Brownian motion, is exactly the same event of the Brownian motion of this. And the non-colliding noise reinforced Brownian motion become like that. Just by using the Brownian motion case, that's time and space scaling, we can get the non-colliding process. And our result is the following. This non-colliding elephant random walk converges to non-colliding reinforced Brownian motion. This is the second case one, as it is fixed. And if Tn is infinity, this converges to this one. We can write the limit process by using the case of Brownian motion. Right? This is the case. And to prove this one, we strong limit theorem. This is a very strong result about this. And the non-colliding elephant random walk, and this is Brownian motion like that. And by sup norm of this term is converged to improbability, very strong convergence. We can use this one. This is explained by Masato yesterday. And by using this result, and the problem is like that. The summation of that is converged to 0, and this result on 0 over 0. This is very complementary. We have to cancel it. The Brownian motion case we can calculate by using Siva function, something very famous functions, and real something we can guess. And this process is difficult, but if you consider just starting point, but the epsilon here, the distance exists, and with some interval, this is positive. Non-colliding probability is positive. Then we can get this convergence. To get this convergence, we have to use this strong limit theorem. This is application of strong limit theorem. Okay? And we can get this one. The point is, the second step is epsilon to 0. And we can get epsilon to, we can do epsilon to 0. It is because the property of X is very nice, and some kind of mixing property or something. If you start another point, the process converges to the similar, same distribution. This kind of thing we use, and we are considering the scaling limit. And first consider this epsilon after some scaling, over to 0 to 0, and we can get this convergence. This is the outline the proof. And the limit process we used by using the previous one, but it is well known that the Dyson's Brownian motion is a eigenvalue process of Hermitian matrix value is like the Brownian motion. This is diagonal part, this off diagonal part, like that. We know that this eigenvalue is exactly a Dyson-Brownian motion with beta equal 2. And we know that this limit process WT, Gaussian process, is a time and space scaling of that. And this is exactly this process. Limit process is associated with the random matrix Amish-Matrix value process, and the diagonal part WWIT, and of diagonal is like that. And on the other hand, W is satisfied this equation. And for each coordinate element of the matrix can be written by this function. We can get this eigenvalue process has a stochastic differential equation. This originally Fisher's process by rule, and we can generate by same argument. This kind of process can be referred by using. We can get the relation between random matrix, Hermitian random matrix, and a stochastic differential equation. And in this case, W is this kind of thing. In general, the stochastic differential is given by the not only eigenvalue process, but also the eigenvector use. But in this case, this is cancel. The limit process is given like that. And just in the Dyson variance plus this drift, very easy to understand. This is the property. And some generalization, we use the relevant random, but this is some thing. Instead of plus and minus 1, we can use we can use IID random value with finite mean and finite variance. And in this case, this is called step reinforced random. In this case, this is exactly generalization. Instead of plus 1 and minus 1, we can use general random variable. In this case, we can generate the result, our result, cell volume 1 to this case, I hope. I have not checked yet, but because we cannot carry Maclaurin formula, but strong limit theorem exists. The same also. And but just using the strong limit theorem, we can get the final result, I hope. And there another interesting problem, and it is better to consider the relation of the random matrix theory in some way. That's all. Thank you for your attention.
Questions?
I have one small one. Can you, in your beginning, you discussed this repelling Brownian motion, right? Can you go back to that slide? The repelling Brownian motion you discussed in the first few slides.
Vicious work. Vicious work. Do you want to understand the vicious work? What is the question? Sorry.
No, just that there was no constant in front of the repelling parameter. I was wondering if it's always one or is something else required there. Maybe I'll ask you later. It's okay.
Yeah, sorry. Sure, please. Please.
Could you elaborate a little more on the connection to random matrix theory?
Matrix theory. Yeah, I explained that. And this is just the relation between Dyson's Brownian motion, non-colliding process, and random matrix theory. And this is wild chamber of A. And we can consider that another wild chamber and the reflection and many one. And okay. And we can generate this result too. Yeah.
So I had a question. So for this diffusion process, so do you have any idea of what the invariant measure is between the gaps?
This is not invariant because this is diverges. But if you put the drift now,
That's gaps.
Yeah, this is time change scaling in the Dyson Brownian motion. Consider and consider the Brownian motion. And if you, but I'm not sure, I minus, sorry, y dx minus 1. Maybe this kind of things. This one. This kind of scan, this becomes the Ornstein-Beck process. And instead of consider a Brownian motion, if you this kind of time scaling, this becomes to the process with Ornstein-Beck. And this is originally discussed in Dyson. And this is just scaling, and this is also some kind of scaling. This is originally same Brownian motion and some time and space scaling. And this is immediate relation each other. From this relation, we can get some kind of asymptotics and ergocity of this process in some sense after scaling.
Other questions? All right, let's thank you again.
Yeah, so.
Thank you.